Welcome to another unit in this preparatory course Mathematics. This time with a unit on derivatives. Well, when we talk about derivatives, that's like one of the key topics in calculus. First of all, what is a derivative? A derivative can, I would say, most easily be understood from a practical perspective as the slope of the function. Well, slope of the function means how much the function changes in this particular point. So that's more or less how we can interpret this. However, here we're not so much calculating the slope directly, but we're using something called the differential quotient. What this is, we see in a moment. Because, well, as we cannot, in most cases, directly get the slope of any function, what we do is we use this differential quotient to get the slope of a tangent to this function. So imagine you have a function, you want to calculate the slope at a specific point. Well, the slope in this specific point is equal to the slope of the line which lies directly on this point, which does not intersect the function, but only touches the function in this particular point. And functions like this, they are called tangents. So if we can find out what the slope of the tangent in a specific point is, then we know the slope of the specific function. So if we want to know what the slope of a polynomial of degree 2 or higher or any other function is, we cannot simply say, okay, take 2 points and calculate the slope via this function here, which works fine enough for linear equations for lines. But we can do this a roundabout way. So we calculate first off, a tangent, not a tangent, but a line through 2 points which also lie on this function. So we just select 2 points which lie on the function. The x1, y1 and the x2, y2. So well, usually this line we get intersects the function 2 times, at least. So what we do now is we move one of the points closer to the other. So we keep one of the 2 points fixed and move the other one increasingly closer to the one which is fixed. So in other words, the distance or the difference measured in the numerator becomes increasingly smaller, but the distance measured in the denominator also becomes increasingly smaller. And if we get close enough, then we almost have 0 distance in the numerator and 0 distance in the denominator. And if we are this close, then we no longer have differences, but we have differentials. And that's what then is called the differential quotient. So if I get as close as possible from one point to the other, if I get one point as close as possible to the other point, then the formula for the slope becomes what we call the differential quotient, or the first derivative in this particular point. Well, that's quite a lot to be doing every time you want to get a slope. That's what, to make our life easier, people determined the first derivatives or rules for the first derivatives for specific types of functions using this particular formula. And those are actually those basic rules of derivation which I mentioned here in this table. And here the main function is the first one, the x to the power of n, which simply is if you take the derivative, n times, and then x to the power of n minus 1. So basically the n, the exponent, is pulled in front, and then you subtract 1 from this exponent. So if I have, as an example, x to the power of 16, I pull the 16 in front, and then I subtract 1 from the 16, giving me 16x to the power of 15. So that's a neat thing, because we can use this same type of function in different other contexts as well. Then we have two additional functions, which are the exponential function and the logarithm. Well, the exponential function as such, so as e to the power of x, this one always stays the same. So no big deal there. But if I have e to the power of n times x, then it's basically I'm writing one of the n's in front of this. So here in the example, if I have e to the power of 2x plus 5, so the plus 5 doesn't matter really, I only get the 2 in front of the x, which I write in front of the exponential function. Okay, and for the logarithm, here, when I have the logarithm, or rather the normal function is logarithm of x, and the derivative thereof is 1 divided by x. If I have n times x, the derivative actually is n divided by x. So here, whatever is above the fraction line in the numerator, that's what was before the n in the logarithm. Okay, so that's basically again with an example here, which tells us in front of the x, in this case it's a 1. So whatever was in the logarithm is now in the denominator. So here in front of the x was a 1. So we have 1 divided by, and what was inside the logarithm was x plus 1. Then finally, we can go back to the second line. Here we have c times any function g. So meaning, when I just multiply any function with a number or with a parameter, I can simply keep this parameter out of my calculations for the first derivative. And after I'm finished with the first derivative, I just multiply this there again. So if I take a look here at 5 times x squared, the 5 I can just pull in front. I only consider x squared. The derivative of x squared is 2x. And then I consider the 5 again. So the derivative of 5x squared is 5 times 2x. So 5 times the derivative of x squared, which then is 10x. Also, an interesting fact, that's the last row here. If I have two functions which are connected with a plus or a minus, I can each derive them separately. So only works with plus and minus. We're going to see how this works with multiplication and division on the next slide. However, with plus and minus, as with, for example, here 5x squared plus x, I can first take the derivative of 5x squared, which is 10, as we've seen above, and then of x. Well, x is x to the power of 1, so I pull the 1 in front. Then I have 1 subtracted from the exponent, so 1 minus 1, leaves me with 1 times x to the power of 0. X to the power of 0 is 1, so I have 1 times 1, which is the 1 we have here as plus 1. So in other words, two functions connected with plus and minus, I can consider each of them separately. Then I have slightly more complex rules of derivation. So first I have the product and the quotient rule. if two functions are connected via multiplication or via division. Product rule, still relatively easy, because here I'm simply, when I have two functions u and v, first derive the first one, keep the second as is, and then I derive the second and keep the first as is. Doesn't matter actually which of the two functions I derive first, as long as I simply switch between those two. So here I have derivative of u, v as is, plus u, v derivative. I could also do this the other way around, because it doesn't matter, because they are connected with a plus in the derivative. That's a little bit different when we talk about the quotient rule, but we're going to do this in a moment. First, let's have a look at the example. Here we have 5x times, in parentheses, x squared minus 1. So first, my first function is the 5x. I derive 5x, which is 5. I keep the x squared minus 1 as is. So I have the first term 5, parentheses, x squared minus 1. Then I go plus. Here I keep the 5x as is. And I derive x squared minus 1, which is simply 2x. Giving me here 5x squared minus 5 plus 10x squared, or if I summarize this, 15x squared minus 5. So here, this is still relatively easy and straightforward. With the product rule, this becomes a bit more complicated, because here I actually have to consider which of the two functions is in the numerator, which is in the denominator. Because I start by deriving the function in the numerator times the function in the nominator, which stays as is, and then I go minus, then I keep the function from the numerator as is, and derive the function from the denominator. So as those two are linked with a minus, here it no longer doesn't matter which of the ones I derive first. Here it's actually essential that I start with deriving the one in the numerator first. And well, after I've done the new numerator of the derivative, I have to divide all of this by the squared denominator. So again, if I consider this for an example, I have here fx being equal to 5x divided by x plus 1. So first I derive 5x, that's only the 5. The denominator function x plus 1 stays as is. And then I have minus the 5x, the numerator function remains as is, and I derive x plus 1, which is only 1. And then I divide all of this by x plus 1 squared. If I then factor out the first brackets, summarize, I get 5 divided by x plus 1 to the power of 2. So that's how you work with functions who are connected by division, or rather one function divided by another function. Then we have only one additional rule, which is the chain rule. Here I have one function which is inserted into another function. Then I have to first determine which is the inside, which is the outside function. Because what I then do is I first calculate the derivative of the outside function. In this derivative, I insert the original inside function again. And then I multiply all of this with the derivative of the inside function. Maybe this becomes a bit clearer when I take a look at the example. Here, my function is in parentheses 5x squared plus 1. And then to the power of 2. So I have basically an inside function, that's a function g, which is 5x squared plus 1, and the outside function, where the variable is g, which is just g squared. So I first take the derivative of the outside function, which is 2g. Instead of g, I'm using again 5x squared plus 1. And then I multiply all of this with the derivative of g, of the inside function. The derivative of 5x squared plus 1 is 10x. So I have 2 times, that's the derivative of the outside function. Then in the parentheses, again, the inside function 5x squared plus 1 times the derivative of the inside function, which is the 10x. This gives in total, as a derivative, 100x3 plus 20x. So this much for the chain rule. And well, if you have the product and the chain rule, you could even determine the quotient rule on your own, because the quotient rule results directly from applying the chain and the product rule. Well, that's generally the rules you apply for derivation. However, there are some ways to make your life a bit easier. And that's what we are going to take a look here. Here, for example, if you have a root function, you have like f of x is the square root of x, you can make your life easier insofar as you can write this function as x to the power of 1/2. Because then you can use the simple function, or the simple formula, for the derivative of x to the power of n, where the n here is simply 1/2. So you draw the 1/2 in front of it, that's 1/2 times x to the power of 1/2, and then minus 1. So you have 1/2 x to the power of minus 1/2. And well, the minus means that you write all the stuff below the fraction line in the denominator. So you have 1/2 times 1 divided by x to the power of 1/2. That's basically nothing else than 1/2 times 1 divided by square root of x, or 1 divided by 2 times square root of x. That's a formula you might have learned in school for the derivative of the root function. Similar to the root, you can also in some ways make your life a bit easier if you have something like 1 divided by x. Because this we can write as x to the power of minus 1. And then, well, again, you pull the minus 1 in front, so you have minus x to the power of minus 1. Again, minus 1 on top of this. So you have minus x to the power of minus 2. And that's nothing else than minus 1 divided by x to the power of 2. And finally, we have like the third example here, which illustrates how working with something like this might make your life a bit easier, even if you apply this in the context of the chain rule. Because here the inner function would be x squared plus 1. The outer function would be the square root, or would be x to the power of 1/2. So here we see the solution on the right side. I would, however, go to the next set of 2 examples, in particular here to the first one, to the function ln of root of x. Again, you could solve this with the chain rule, but you could also make your life a bit easier. If you think about that, square root of x is actually x to the power of 1/2, you can use this to rewrite ln of square root of x as 1/2 times ln x. And well, 1/2 times ln x, the derivative is simply 1/2 times 1 divided by x. So it's simply 1 divided by 2x. And here you see on the right, well, first of the solution I mentioned, and also how this would look like if you do this with the chain rule. So in some cases, thinking about this might make your life a bit easier. And finally, the last example, f of x equal to x times e to the power of x squared. This is just an illustration to show you what if I actually have a product rule, which I need to apply, and one part of this requires a chain rule, which is the e to the power of x squared. So in this case, you simply start with the product rule. So I derive x, which is 1, keep the e to the power of x squared as is, then I keep the x, then I need the derivative of e to the power of x squared. Then here, in this part, I'm taking like one step back and applying here the chain rule. So I have the outside function, the exponential function, which stays as is. So I have here e to the power of x squared. As I said, outside function remains the same. So I insert the inside function x squared again. And take all of this multiplied with the derivative of the inside function, which here is 2x. So in this case, I then first applied the product rule. At the point where I can no longer carry on, I then applied the chain rule. So you work your way step by step by step by first using one rule, which explains like the general behavior, then you go into more detail, step by step. So this way you can calculate derivatives relatively easy, even from relatively complex functions. Well, this then concludes this session. So see you again in the next unit, and I say goodbye. Until next time.